Hello, hi everybody. You all can hear me well and clear. Mukul Pal here. Okay, great. So we can hear each other. You can hear me well. That's great. Welcome to the talk. And thank you for inviting me to speak on the subject. As you can see, I'm speaking on general AI, and this is not something which is very clear and obvious as a subject or as a line of study. And for those who are not aware, just to briefly explain what general AI is, it is a lot about generalization. It's a lot about um, strong AI, and strong and weak AI have many ways which we can classify them. But general AI is generally defined as AI that can do things which human beings can do. So, human intelligence or um, something which is linked um, with conversation, something which is linked with visualization, something which human beings can do, or human tasks is what general AI is. But again, when we do something like humans do, then we necessarily are not going to stop there, right? We will move towards super intelligence, because you cannot say that you are doing all the tasks which human beings do, and so now stop, and now we don't have to become super intelligent. So general AI is is all that category which goes from human related task and ahead. And the reason I don't know why it's called strong AI, but I think it's more of a of matter of this capability that determines weak AI from strong AI. Now weak AI is, or narrow AI is something which is to do with domain specific knowledge. It is something which is n- thought about, something which helps human beings, not necessarily cross human intelligence. So this is the broad difference between general AI, strong AI, and weak AI. Let's get into the subject ahead. Let me see how I can. Okay. There are three stages of my presentation. Um, one is conceptualizing intelligence. Then after we conceptualize intelligence, because ultimately we have to define what is intelligence. We cannot talk about how machines will become smarter than human beings without understanding what is intelligence. Then we go into um, into talking about um, how to abstract that intelligence, how to specify that intelligence. And after that we go to assimilation is the final goal, because if you think about Siri, and Siri is talking to you and listening to you, what is Siri doing is navigation. It is fetching information for you. And assimilation is where it doesn't just navigate, it knows it. And when it knows it, it can talk to you. So that level of conversation that a machine can hold um, can only happen if there is assimilation of knowledge. Now we are talking a bit of future here, and my discussion is about the future, because general AI, as you will see in my presentation today, is Wikipedia talks about it, about building brains. And I'm contesting that idea, because I'm saying that general AI or human intelligence is not about building brains. That's a step. But the general AI or strong AI is about understanding complexity, understanding nature, um, doing things which do not hit barriers of computation. So this is where my talk um, uh, is ahead in terms of the context. Um, so I may occasionally ask you to let me know whether you can still hear me and you get it. So please feel free to keep those messages coming, because I don't want to have a monologue here. So are we clear till now what I am talking about? Okay, great. So conceptualizing intelligence is starts with this thinker, um, uh, and Proust, Proust, and this is a Scientific American article where they are talking about cautiousness, and here the thinker is looking at himself and imagining um, a machine that looks like him. So, when I saw this article like a few years back, it left a very um, strong impact on me, because just asking such questions about cautiousness is quite a tall task for machines, and uh, somewhere it is an aspiration for some of the thinkers on AI to build such machines, and on the other side, ethics and other questions about the fear of AI that it can conquer us. So these are two conflicting thoughts, and I'm not going into this, but consciousness is a tall benchmark to teach a machine. And one of the things which the article mentioned about consciousness was that a machine is cautious when it can observe itself. So the consciousness is somewhere connected to being aware of itself. And when you're aware of itself, then you have definitely crossed an intelligence level. You understand a lot of things. You're aware of your surroundings, and so that, I thought, uh, was a very defining feature for what general AI could become. It could become cautious about itself. And then there are some other articles and some other research papers. I've taken excerpts from different papers. So my presentation is about excerpts of papers. I'm taking you, every slide is a paper. So this is a paper uh, uh, by Lowenstein. Lowenstein is one of the biggest researchers on uh, intertemporal choices. How we choose to smoke, knowing very well that tomorrow it is going to harm us. How we choose to indulge in instant gratification, knowing that delayed gratification is the thing to do. So this inability for us to measure our choices in context of a bad future or worse outcome is the subject of intertemporal choices, and it was created in 1850s by a man called John Ray, who was the predecessor of Adam Smith. It was a subject ahead of its time, even after 1850s. It's still a subject which behavioral finance does not talk about, but behavioral finance is based on the idea how human beings indulge in instant gratification, discounting delayed gratification. How do we make poor choices, knowing that, so we discount the future more. Our ability to understand its risk and returns is less. So that's the subject. So in that paper, one of the temporal preferences paper, which if you are a behavioral finance person, maybe you have read it. If you have not read it, if you are interested in the subject, you should read that paper. And in this paper, he has a brief piece which talks about what is intelligence. So he talks about three things. He talks about it remains relatively constant across time within a particular individual. It predicts behavior across a wide range of situations, and different measures of it correlate highly with one another. Now, if you think about it, there is intelligence and it has different ways to measure, and the metrics of that intelligence are very correlated with each other. So at least when you are intelligent, you do not know to be intelligent in different metrics, because your different measures of intelligence should point to the similar intelligence, which means that the whole idea of statistically making you intelligent is defeated once you reach a stage of intelligence. This is I'm talking philosophy here, and I want to my aim is to share my thinking, because we are going to build this into a more concrete next session, and which will be more about application, more about how asset management as a business is going to be disrupted by machines, how they're already doing it. So this, I thought, was a good foundational layer on that. So this is Lowenstein's explanation. I think he cited something, but I've not gone through the citation, but this I thought was very interesting. And then this is another paper which is called Human Problem Solving, 1970, written by Herbert Simon. Herbert Simon is 1976 Nobel Prize winner. Herbert Simon is father of AI. Herbert Simon is father of behavioral finance. He's written 30 books, 1,000 research papers, and some of them papers were written as academic debates with Mandelbrot. So it's a big luminary, and he has driven me with his thought process. So I consider him one of the biggest thinkers who's inspired me. I have a quote on my blog with Herbert Simon, and so Herbert Simon in this paper is talking about thumb rules. He's talking about how intelligence is programmable, how intelligence is a set of rules, how when the program learns that rules, the magic is over, right? And there are some people who have written recently in a book which says the idea that died. I have this book here with me. It's called This Idea Must Die. It's written by John Brockman, and in this book is based on the idea of Max Planck, who says that science progresses with the death or funerals of the people who drive that science. Only that is how science progresses, because we don't just align together and say, okay, let's agree to this new theory which is very good, so we don't just do that. So somewhere we are always working with old science, and we do not really and consensus on a scientific theory doesn't make it true, right? It doesn't make it it's most popular, but it may not be the most significant, right? So we have already seen it. A lot of theories rot, and then somebody finds it 60 years later. And I want to talk about some of these theories, and if in case I forget, I'll mention now. Louis Bachelier wrote his paper on speculation in options in 1900, and he had an error in his PhD paper, and then he got his PhD professor were upset with him, and he did not get the right job, and he was frustrated all his life. And then 60 years later, Paul Samuelson finds that paper and he creates modern finance. So the modern finance that you're talking about, this portfolio management and asset management and Sharpe ratios and all these things are somewhere buried in Paul Samuelson picking up that 1900 paper of Louis Bachelier, which had an error. So, the whole idea is that science is only progresses with the death of people or scientific proponents, and it doesn't really has a natural consensus to beautiful theories. Now, the reason I'm pointing out this paper is because in this paper, Herbert Simon and Neville are pointing out that intelligence or some human intelligence is programmable, and if it is programmable, then suddenly the magic out of that intelligence gets over. And when the magic gets over, then you realize it's just thumb rules. It's simple. It's not so complicated. There's no high science here. Machines can be taught programmable intelligence. So the paper talks about thumb rules, and the paper is even cited today when we talk about taking out the buzz from AI or taking the aura from AI. That this is a very these are very uh, commoditized things. If you teach something to do intelligently, then it's already programmed. It is not intelligent anymore. It has to learn something new. It has to learn something new. It has to be on a constant quest of acquiring intelligence, and that is how it becomes intelligent, when it can constantly keep itself intelligent. So the reason I'm pointing this work is to highlight that the difference between general AI and weak AI, narrow AI, what you see today is going to become commoditized because it'll be programmed and it'll start doing it. And when it start doing it, then that is no more a benchmark of intelligence. So this is still the challenge for AI today, that it is not reached a level where it can become cross those barriers where it can teach itself, right? So this is the reason I'm pointing this paper. Then this is what I just highlighted about Max Planck, where he says that scientific theories evolve. It says that here uh, in the third line from the bottom, what does happen is that its opponents gradually die out, and that the growing generation is familiarized with the ideas from the beginning. Another instance of the fact that the future lies with the youth. So the whole idea of funerals in context of scientific theories. So this is the part, and this is another interesting piece I want to show you. Uh, which is called the Campbell and Goodhart debate. Now, this is also a very important piece in terms of understanding that why weak AI is somewhere limited in its scope. The reason weak AI is limited in its scope is also because it suffers from the Goodhart's law, which is that if you know a metric and if a measure starts to get used, it'll become irrelevant. And now, this is a very large claim, but if you think about it, making money on price earning models, 1970s have been written about, and 1970s they say price earning is not so significant as a tool. The whole idea of fundamentally using ratios to predict markets. The more the ratios come, the more we see they become less and less valuable, because somewhere they suffer from the curse that if everybody's going to follow them, it's going to become irrelevant, right? And that is why some of these thinkers talk about AI as it should be said that a computers doing interesting things can be also called AI, and we should not give that aura of AI if it is doing smart things or interesting things. So this is a really uh, um a resistance for intelligence to go up, because we are somewhere indulging in the similar feeling which we had with variables, which we said, oh, this is a good indicator, it's going to work, and then it fails. So we are going to do smart things, and programs will learn it, and then it'll we have to move to the next level, right? So this is another thing about variables, and why general AI is a future, because things will get commoditized. Okay, next slide. So this is a kind of summary to my first session, and this is where as I said, I'm conceptualizing in intelligence, and I started with cautiousness, and how can something be cautious? First, it has to be intelligent. How can something be intelligent? It has to be programmable. How is something programmable? It has to be scientific. And if it is scientific, then is it the dead science? Is it the new science? There is a suffering which comes with science, because we may stick on to redundant science for long, and the new science is not there. If you read about the history of deep learning, you'll realize that um, that some of the thinkers like Terry, uh, talks about in his book on deep learning, which is a great book which I strongly urge you to read if you are interested in the history of neural networks. And in that book, he, not in one time, but in multiple time, he talks about Minsky. And he says that Minsky did such a disservice to AI, and because of him, the research got delayed by 10 years. And then he also says that it was lucky for him that it it got delayed for 10 years, because uh, he could harness that delay for the benefit of his career, because he came in a time when he could actually contribute. But he also basically um, accosted Minsky in a conference and say that, please admit that you are the devil. So it's kind of crazy things you read about how scientific theories do not evolve, because the big leaders are so married into their process that they just become a roadblock themselves. So the whole idea of the suffering that comes because a scientific theory is relevant or not relevant, and we are working with 30-year-old work, is that suffering. If a machine is cautious, then it has to suffer. Now this is a very philosophical thing I'm saying, that cautiousness becomes complete if a machine understands the redundancy of science. And if it does not understand the redundancy of science, then it gets into a loop, and it becomes irrelevant, and it does not become cautious, and it has to start the path all over again. So this is somewhere the point of intelligence being dynamic. This is the point of intelligence being a process getting consistently smarter, a process being cautious about itself, a process which is hard to commoditize, a process that can assimilate. So this is where the conceptualization comes about what intelligence should be. Are you all with me still now? I will move to the second stage. Great. So now uh, we talk about generalizing intelligence. Now, if it is already so dynamic, if it has an aspiration to be cautious, it cannot be really bogged down by roadblocks. It cannot be really. It has to learn how to hump. It has to learn. It has to learn a lot of things, and if it has to learn a lot of things, it cannot get lost in specific. It cannot sit in the cannot get sit it cannot get stuck in the local minima. It has to be able to see the global minima. It has to see the global minima of one domain, go to another domain, understand the global minima, map these structures of the surfaces of the data, combine data surfaces. So it has to generalize. And this is also what Master Algo, which is another, uh, I would say, historical book uh, by Pedro Domingo, and he talks about the history of machine learning, and he talks about how things got evolved, how support vector machines happened, how they were trying to solve something, how they got stuck there. So it's a great piece of, I would say, um, foundations of statistics that went into machine learning. And and it also talks about this vision of a master algorithm which can learn from different subset of algorithms, different tools. It can drop tools, it can take variable, go to new variables. So this is where the aspiration of general AI is. So how do we generalize intelligence now? Again, I'm going to talk about different ideas here, and this idea of generalizing intelligence, and somewhere my contesting of what a general AI is and the definition of general AI. When we raise money from a VC, we say we are a general AI company. They say, why are you a general AI company? They say we are a general AI company because we our capability is universal. We can work from one domain to another. We can see behavior. We can understand a flock of bird. We can understand complexity. We can redefine complexity. We understand these things. That's why we are general AI, because AI which understands nature or complex systems has to be general AI. So they had a difficult time grasping that, because the reference for them was what is public knowledge, and public knowledge is that general AI is building brains. So we were like, we had this conflict about, uh, you know, that you should not say you're a general AI company. So of course that whole discourse changed when the VC also agreed and started referring to us as that, or becoming less reluctant to this thing. So it was evolution. But for me, it was very clear that brain cannot be an end of general AI. It has to be the beginning of general AI, when we can build brains. Now, if you are aware of neural networks, and you'll understand that how the whole neural networks has evolved from understanding how the brain works and connecting it to the eyes, and understanding how the brain visualizes, how the brain sees what is to be seen. And this whole process has led to the evolution of general of of neural networks. Now, neural networks is ultimately also considered, or was considered, a general AI benchmark, because neurons are are computation. Synapses is computation. So you have a brain that processes, that computes, helps make a decision. So it's intelligent, and hence the whole idea of human intelligence connected with the brain. Now, for me, the idea, the challenging part was here was that coming from a capital market background, I saw so much herding. Everybody wants to sell at the same time, everybody wants to buy at the same time. So there is such a animal spirits behavior that I could not align myself to this definition. And I said, how can something so herding, something which is designed to make a bad decision, be intelligence? So I always thought that, okay, what can understand this herding, or what creates this herding, has to be more intelligent, and that should be the definition of general AI, right? So this is my quest of uh, redefining general AI as something that can understand nature. And of course, there's a whole 15 years of work in this area, and I'm still the singular proponent of my theories, and you can help me get visible 30 years from now. but at least I'm proposing this definition, right? Or at least something which is an extension of a definition. Now, this article about brain is in Scientific American, talks about, it's just by chance I'm citing more Scientific American because some of these theories are very well presented. Plus, it's a 175-year-old journal. It has a legacy, and I think that some quality work uh, has come out, at least, which is influencing me right now from these journals. So in this article, the author talks about the physical limitations of brain. He says that brain has a limit, has a physical limit, and that is why there is a limit of what can be expected from the brain. So this is the whole idea it's a kind of throwing a spanner in the definition of general AI, which is about, let's build a brain and we'll become intelligent, right? Let's understand a mapping of a brain, and then we can give a brain to everybody and everybody will become intelligent. So somewhere it's challenging that hypothesis. And now jumping from there to this comic book feature, and the reason I wanted to highlight this was to talk about Boltzmann brains. Now, Boltzmann brains is an idea which was father of thermodynamics, Ludwig Boltzmann, and who said, that entropy, second law of thermodynamics, entropy is always changing. So if entropy is always changing, and in universe it's always changing and it's always increasing, then temperature is going to be constant in a certain part of universe. And if it's cooling at a similar rate, then Boltzmann said that it's very hard for human beings to exist, because human beings exist because there is a hot sun next to a cold earth, and that's such a rare or such an error to happen, that it was because of this random fluctuation that human beings came into existence. So life as we know it is an error. I've written about it, it's on my blog, and if you read about Boltzmann brain, you'll can relate to the idea I'm talking about. So Boltzmann brain is this brain which comes and exists and say, I exist, and then it vanishes. So that's where the idea of Boltzmann brain came from. And but the contrast was that if you open the door, you still see order. You can go from your house to the main road. The main road, you can take a car, and then you can go another city, and then there's so much order which beats the whole idea of the entropy change. So somewhere life is existing because of the failure of the second law of thermodynamics. So this is where I'm bringing the idea of an error. So I'm coming from a brain, limitation of a brain, to the error, which is kind of hard of can get one very depressive, that how are human beings an error of nature. Now, of course, they found out that these errors are not that infrequent, they are very frequent, there are more life forms, and suddenly we have a different definition of error. We start looking uh, at the failure of second law in a different context. That maybe there is more to this failure. What is the other thing driving this? How does life exist? And that's where the whole paper of Erwin Schrodinger comes, where he's talking about what is life, right? And so I'll come back to that paper. Are you still with me? Is it too philosophical? No. Are you understanding what I'm saying? Okay, great. So this is another paper which is talking about, which is written by Francis Jacob. Francis Jacob um, uh, was a geneticist, and a very early paper, and he basically was in time with McCulloch. McCulloch was the one of the first thinkers who she talked about jumping genes. She said how learning in nature, because if you had to, if nature had to work in a sequential process, then it would have taken a lot of time for human beings to arrive. So nature's decided to speed the process, and in the early cases it has seen that genes were jumping from one species to another. So knowledge was jumping from one species to another, and suddenly there was such a speed, which scientists now talk about, that you can read about it in the Quanta magazine. Quanta is doing great work in mathematics and science, and it's strong. I strongly urge you to visit their website. And they don't have a print edition, but they just have an online version, and it is run by James Simon Foundation. And James Simon is coming from the Renaissance background, and I'm assuming you know about Renaissance technology, the most successful hedge funds of all time. So in that they talk, in that Quantum magazine, there are scientists interviews, and they talk about how did nature do it so fast. The nature did it so fast because it was not working sequentially; it was jumping genes initially. And so Jacob, in this article, in this research paper, uh, talks about how nature is a tinkerer. It can mix things, combine things, be creative about it. And while it is creatively doing things, it is speeding up evolution. And the reason I'm talking about it is in context of a limitation of a brain, in context of life being an error, and in context of nature thriving despite error. So this is how nature works. And again, the quest of general AI to understand how nature works, how nature is modeled, how complexity happens. This is what other paper I was talking about, what is life. And in this paper, uh, Schrodinger is talking about what is life and how subatomic structures are connected to classical structures. The whole quest of unifying science of quantum physics with the Newtonian physics, the whole idea of how can the quantum realm drive the classical realm. Now, this question, we don't have the answer to it, but it is connected to the question of how did life form? How does low entropy happen in high entropy? How does something random happen and which creates life? So what is life is another of the big papers which talks about nature and entropy and errors and disorder and order, and how life is somewhere connected, or life or system or organism which is intelligent is connected as it extracts order from disorder. If something can extract order from disorder, life happens. Now, it's somewhere like saying extracting value from errors is can be defined as intelligence. If you can despite the noise make sense, that's intelligence. So this is where I come to Herbert Simon's paper again. In Herbert Simon's paper, Architecture of Complexity, that's another paper which has stayed with me and driven me all these years. And maybe I read it in 2007 the first time, and I've revisited it. And the most beautiful thing in this paper is that it says that complexity is intrinsically simple and hierarchical. It is simple structures nested on each other that makes complexity. So it's somewhere saying that simple structures create disorder. Now that's a very profound thing to say, but that's what I'm building on in terms of the how error can be a foundation, or how simplicity can be a foundation for complexity, and how error can be sitting on something very simple and structural, right? And here, mind it, he's not talking about information. We are not sitting on information. We are sitting on structure. We are sitting on geometry. We are sitting on architecture. We're not sitting on information. So that is why general AI is somewhere not about information per se. It's about the structure of information. No, this is why this conversation means I'm somewhere talking about what's already being written. Of course, my belief is new into this, and I've added some layers to it. But what I'm saying is somewhere said 30 years back. Kenneth Boulding has talked about it. Information goes through stages of relevance and irrelevance. Now, what I was talking about, Campbell and Goodhart's law, is about a variable becoming irrelevant. If you leave that variable, society doesn't talk about it, then it will become relevant again. So, in context of stock market, this is a very important philosophy to understand, that are you really doing service to yourself by following an indicator? Should be you rather be following a structure? Should be you be understanding structure of information, architecture of information, right? So this is why I'm highlighting Architecture of Complexity paper, a great paper to read. So this summarizes my part 2, where I made this illustration here, and I'm saying that brain has a limitation for intelligence. Boltzmann brain is an error, or it tells that we should not have existed. And then Architecture of Complexity says error or complexity is standing on a simple and hierarchical structure, and nature thrives on error because it tinkers. It is not working sequentially, computationally. It is not dying if there is more or less computation. It is computation agnostic, and it is processing and learning. It is so intelligent that it doesn't really need to have give me the exact training data set, because I'm going to learn from it, I'm going to mine it, I'm going to become smart in it. Nature is not doing that. And then the breakdown on the second law of thermodynamics. So it's somewhere the brain has limitations. So why did second law of thermodynamics fail, and why does life happen, is not a capability of the brain to process and brain to come to these answers. It is, if we keep modeling brain, we may not reach those answers. What we have to instead model is nature, and what we have to model, understand, how does nature thrive on error, how does it simplify. So this is where the I build the idea of intelligence as a concept, to how errors have to be simplified and nature has to be modeled as somewhere the definition of strong AI or general AI. So now I'll go to the third part, which is about assimilation. Are you still guys with me, or is it getting difficult, or are you still understanding where I'm going with this? Okay, so a difficult, yes, good. So some difficulty here. Great, awesome. Thank you for the messages. Uh, Now we go to assimilation. So we want to build super intelligence, we want to build general intelligence, we want to build general AI, and this is assimilation now. As I said, Siri is navigating, it is not assimilating. If you would not have known, then I'm Mukul Pal, or if you do not know that I'm Mukul Pal, if I was a computer or a machine, and if I'm convincing you that I'm Mukul Pal, then I've then this machine, that is me, has passed the Turing test. And somewhere the Turing test is also about assimilation, because it is not about just proving that I'm a human. That is one stage. But having a conversation with you on any subject you want, whether it is science or it's philosophy or it is mathematics or it is markets or it's behavior, whatever it is, if I am know all, then somewhere that is assimilation, because I don't need to go and hunt for information. I can talk to you about it. So assimilation is the future of machines, where you will have conversational machines. We are building one now. We are building a conversational machine which will start talking to you, understanding you, what you need from your portfolio, and we will furnish it to you. So we are building assimilating machines. So I'm talking about assimilation now. Assimilation somewhere brings me to the idea of what the future will be, because assimilate, I'm talking about tools per se now, or how tools will evolve in the future, that assimilation will be possible. Because ultimately, why do we need assimilation? We need assimilation because we have to put machines in a quest or a loop of intelligence. So if they pass a test of intelligence, they question them again, they challenge again. The Go, which was beaten, there were two Goes. One was a Go which fought with a human being, and then there was a Go which was a machine that fought with a machine. So the future is about machines fighting with machines, because we are putting intelligence on drugs. So we are not just happy with the fact that, okay, we became the smartest investor in the world. Then we have to compete with the machines fighting with machines, so that machines survival is linked how relevant they are if they can beat other machines. So it's a consistent quest. It's not going to stop by saying, okay, you become the smartest investor, you become the smartest fund. But now, if you see, some of the hedge funds are really driving the quant process to the next stage. It's machine-based work, and ultimately, there are a lot of assumptions where how machines can work. Some people are still getting very computational with data. Get me more data. Get me more data. They have so much data. Let me mine the data. So that's one process to do it. But again, the machines I'm talking about are working at a surface level. They have to understand from the surface what's inside the water. So this paper is a recent paper, and I thought it was relevant. It talks about algorithms in future capital markets, and what it is saying is that there are kind of three directions where the future will be, and it's also about harnessing those three directions together in a focused way, which is that you work on computational statistics, you are working on uh, machine learning and genetic algorithms are about how nature optimizes, and it's a beautiful subject. So that's the second part. And the third part is multi-agent system, where you are simulating how the capital market working like a flock of birds, how capital market is working like a forest fire, how capital market is working like a traffic jam, how agents interact. So this is a part of the control systems, or it's called MAS. So these three things together is where um, where there are where the future is defined to be, and somewhere at the heart of it is the probability at the heart of it. Because if you think about it, what is the most important variable for science? The most important variable for science is probability. What if probability itself was very dynamic? What if probability itself was noisy? So understanding probability, or the dynamism of probability, this is how I see it. But the paper talks about these three big large circles, but I see probability sitting in the inside and feeding backward and forward into these systems. So this is a, a kind of toolbox for uh, moving ahead in terms of AI and machine learning to build intelligent systems, or which can be in a constant quest of learning. This is a this is my version of a neural network. Maybe you understand it or you don't understand it, but in briefly, I'll explain you how neural network works. Neural network has I, which is input data, and it is thrown onto some nodes which get some information, and they pass that information, their understanding of their information, onto hidden nodes. And after hidden nodes process that information, they pass it to an output node which sees how your output is a cat, and what you showed the uh, node was an image of a cat. Could it classify? Could it not classify? Right? So this is how neural networks are. It training, it is able to see, it's able to classify, it's able to read lips and write the text. It's able to drive cars. It's able to do things which are were thought not programmable, because of this learning which is inspired from an eye and a brain. How does a brain function, and how does an eye see? How does the eye send the message to the brain? Now this is where my version of neural network is, where I'm saying that nature is a closed system. So somewhere the input is transforming itself into something else at a different time. Now you can call it output, but it is about anticipation. It's about dynamism. It's about output sending feedback back to understand input, and input non-linearly feeding back into another form of input. Like, so the closed system functioning, unlike neural network where you have to throw some information, in a closed system like nature, you're not throwing it some information, it already has that information. So if it already has that information, it is processing inside only, it doesn't need any new information. So this whole ability to anticipate, whole ability to model nature is what I'm showing here as a as a prototype of a model. Now, this is the kind of prototype we are working on. Our system is a closed system where we do not get any external information, and we understand probabilities in a closed system to anticipate the system. So this is where our work is. So in conclusion, uh, general AI or human intelligence above human intelligence is data light. It can learn from proxy data. It doesn't need the exact data. It is computation light. It does not need give me more power to more GPUs to understand and I can give you insight. No, it is computationally light. It doesn't need variables. It is variable agnostic. It is anticipatory. It is error embracing. It is a tinkerer because it is modeling nature, and it has structure. It has architecture. It has substructures. So this is why general AI is the future. I'll pause here. I know I've stretched a little bit on the time, so if any questions, any thoughts, observations. So if there is any question, if there is any observation, did you understand? Did you understand half of it? Did you understand 80% of what I'm saying? Um, do you align with me on this philosophy of general AI? Do you disagree with me on this process? It's good to disagree. Okay, so um, okay, that's good to know in terms of the broader view of what I'm saying, that it doesn't seem to um, um, too too much um, nonsense. It seems common sense. It's so such a difficulty in separating what's nonsense from common sense, right? So if you look at markets, they are so um, going up in a in a biggest pandemic seems nonsense, and seems means nonsensical, or maybe nonsense is not the right word, but it seems hard to explain, and sometimes it's easy to explain. And the neural networks also have a biggest challenge in terms of explanation. How does it do what it does, right? Um, so I don't know whether general AI will do this explanation, but general AI is more about outcome in terms of anticipatory outcomes, right? So yeah. uh, yeah. Go, Government is an important error minimizing or error maximizing. Everything we do as a society is either increasing errors or decreasing errors, and so errors are going to stay in the system, and we have to build system which can work through and with the errors. How do we understand errors and noise? Okay. So I guess that's it. So if any other questions, please feel free to mail me, or mail Aline, and I'll prepare a bibliography and I'll send it over to you in case you're interested to read. I'll also post it, and I'm sure this video will be available for audit. Thank you for your time and patience to listen to my talk. Thank you very much.